Okay, let's start. Do you have any questions? All right. So last time we were discussing the idea of a Brown motion. So WT as a process is a Brown motion if it starts at 0, it has stationary increment, meaning the difference between any two time points has a normal distribution, mean 0, variance t minus s, and it has independent increments. Meaning if you have time points s less than t less than u, then as long as they are not overlapping, then the difference are independent. Okay, so now where do we get Brown motion from? Brown motion comes from, right, taking the limit of the binomial model as time step goes to 0. Okay, so we won't repeat the process of how the limit behaves, but basically as time step goes to 0, what we have is we obtained a model, the Black-Scholes model, for the log return, right, of a stock. Okay, what is a log return, right? Log return is the return, right, the natural log of, let's do this, st plus dt over st, all right? And that will be have a mean mu and has a variance sigma. Okay, so here dt is a very small time interval. In fact, right, it will, for a lot of context, is like 0. So in fact, it's not a physical quantity. All right. I mean, if you want to understand what's going on, you can just add an ET and pretend that's like 0.01 or something. But in terms of proper calculus, these are not some physical quantity, right? They're just almost 0. They're called differentials. Okay, this is the time differential. Okay, like a split second or something, a split second. All right. So this notation, right, will be strange at first, but you always want to keep in mind what they mean. So this is the change in the stock price as time moves in a split second. So this is the stock differential, right? Stock price differential. Differential means difference, means change. That's all. Right? And then we introduce notation DWT, which is this is Brownian motion, right? Differential. Okay. So all in all, oh, and by the way, right? This law is the natural law. Okay, this is natural law. So there's no log-based 10 used in this class, which is right, LOG for natural law. So notice that this quantity by the rule of the log becomes log of st plus dt minus log of st, okay, which is mu dt plus sigma dwt. In other words, this will be log d log of st, which is mu dt plus sigma dwt. Okay. So this will be, again, right, from here to here is the same model. But if you write it out this way, at least you understand what's going on. Okay. But of course, abstractly, people always write like this. So your one of your responsibility is to be able to understand what this means by expanding like that. Again, right, the meaning is very simple. This is a log return over a split second, right? It takes on the return rate, right? This is the return rate. Okay. And this is called the volatility. Now, this is like a shock. The Brownian motion, you cannot know what it's going to do next. So, right, this is the shock, this is the noise. Shock from the market. Okay, from market actions. So is a very intuitive model where it says your return, right, always has an average rate. And then the volatility, right, gets amplified. Also, or the market shock, right, gets amplified by your volatility coefficient. Okay, and of course you see the shock in general has mean 0, and the variance, right, equals to the duration of that split second. Okay. We'll talk about, right, how to work with this model soon, which is basically stochastic calculus. But before that, let me just say, right, that this implies, all right, first of all, here, basic rules of stochastic, basic rules of differential. If there's one rule that you must always remember, right? There are many rules you will have to remember from now on. But the first one very basic rule is that let me say, okay, this. What does this say? This says that, again, what the integral means sum, okay? D means small change. This is big change. This is just saying if you add small changes, you get the overall net change. And this is true for any process. So that's why I write F. Okay. Any process satisfies this. Because again, right, basically, if you add all the small changes, you just get the net change. There's nothing like, earth-shattering about it. So applying though, right, applying this, okay, again, right, you see the integral, it just means sum, okay? All these things are very intuitive, but we need to kind of keep those in mind. So if we add this up, okay, so let's add up both sides. Add up both sides, let's say from 0 to t, okay? D log SU is mu du sigma dwu. All right. So from here to here, basically I say, right, the differentials are equal, the net change, the change are equal everywhere. So if I add up all the change, I also get the equal net change. Any question? What do I get out of this, right? Now again, right, pay attention. This notation means the change, right, differential of the log. This is not, right? So the D applies to the log. So from this rule, right, I get, this is log of st minus log of s0, which is, this is just mu. This is your good old integral, okay? Nothing changed. Mu times t, and then this is sigma wt minus w0. Okay? Any question? Remember, w0 is 0, okay? One of the basic rule of prime motion always start at 0. So this will be log of st over s0 is mu times t plus sigma times wt. This is natural log, okay? So I get st is s0 e to mu t plus sigma times wt. So this is the model for the log price, for the price of the log, price of stock price model. And of course, this is Black-Scholes model, okay? Stock price Black-Scholes model. That is correct. Now, of course, the notation might get a little bit, exactly. And so, right. So yes, it's mu times t here, because mu is a constant, right? The sub t means it's a process at time t. Yes. So yeah, I mean, sometimes the notation can be a little, right? This is w sub t. It's not w times t, because I never defined an object called w, okay? W is a, process, all right? So it's a function of time, yeah. Of course, right? So for that reason, later on, you'll see something like this. I will always write WTWT. I will never write WTT. I could, but that, this is WT times T, okay? So pay attention to what object is which. All right. So what I want to say is, right, from the log return model, we also obtain the stock price model, okay? In between, there is this mysterious object of the percentage return that we'll get to, okay? Which is the change, right, in the stock divided by the stock. Okay. What is this? That's the goal. And the reason is, right, you will see that mysteriously percentage return will be like this. In other words, percentage return is always higher than log return. the rate. And the higher rate, right, the high average rate is exactly 1/2 times the volatility square, or 1/2 times the variance. Okay, so why? Okay, and that is the goal of developing on the stochastic calculus rule. We'll get there later. Okay, so this is we'll get this. But before that, I want to do something even more basic because it's going to be required for your homework this week. Let's do basic before that, right? Let's do basic uh, probabilistic computation for Black-Scholes model. Okay. So I'll ask you to accept this for now, that there is the idea of risk neutral, okay, in the Black-Scholes model as well, because the idea of risk neutral, right, applies to any model. Of course, the challenge is to understand what does it mean to be risk neutral in this kind of context, which that's why I asked you to accept. I'm not explaining that at the moment. But what I want you to accept is that the risk neutral model will be ST is S0 e to R minus 1/2 sigma square times T plus sigma times W, like that. Okay. So it's not actually anything very far flung from this. All I'm saying is, right, this is a Brownian motion. This W tilde is also a Brownian motion. Okay. There are two different Brownian motions. Uh, there are two different Brownian motions. Okay. For your purpose, it doesn't really matter. You never really try to work from one to the other so much. So we will explain the relation, but it doesn't matter. Okay. But so this is a Brownian motion. What I'm claiming is that under the risk neutral framework, the rate of return, okay, of the of the um, of the log, okay, of the log return is a risk-free rate minus 1/2 sigma square. Okay, it's kind of amazing that the return of the log, okay, the log return average rate under risk neutral model is actually lower than the risk-free rate. But anyway, right, these are financial components that we'll explain later. I want to do the math here, which is the working with the expectation, that kind of thing with the model. So accept this, okay? Nothing too mysterious about this W tilde. Just think of it as a Brownian motion, okay? A Brownian motion under the risk neutral framework, okay? Its meaning is exactly like you change from P to Q. This is the P model. This is the Q model in terms of the binomial model, okay? But my interest is something like this. And in general, right? Let's say in general, you may be asked to work with this kind of object. Sorry, my iPad's acting up. Okay, so in general, you may be asked to deal with this kind of calculation. Let's say ST is S0 e to mu t plus sigma W tilde t. All right. And you ask for a kind of object like the expectation of ST. Okay. So how do you do this kind of calculation? Well, so let's take a look, right? And of course, if you can do this, then this is just a particular case because here mu is equal to this object. So so by E tilde, right? It's just exactly like the risk neutral expectation that you're used to doing, where, right, we just say that under E tilde, This is a Brownian motion. So to do this calculation, you see it's going to be this. And then, well, when you take expectation, right, in this context, you must pay attention to what is constant and what's random. The only thing that's random in this whole expression is the Brownian motion. Everything else are constants or deterministic. So in other words, you can factor out okay. So what you're dealing with is something like expectation of a normal, let's say sigma here, with mean 0 and variance t. Why? Because the Brownian motion, right? You can look at W tilde t as W tilde t minus W0, W tilde 0, because the Brownian motion starts at 0, right? And by the property of Brownian motion, okay, it is has mean 0 and variance t minus s. S here being 0, so it has mean 0 and variance t. Okay. And here, right, this calculation in of itself may be already an exercise, okay, in a 477 class. It's referred to something called the moment generating function. Of a normal with mean mu and variance sigma square. Okay, that says that expectation of e to the t mu, sorry, normal mean mu and variance sigma square will be e to the t times mu plus 1/2 t squared sigma square. Okay. You can look up how to work this out. It is a completeness square kind of procedure. So I don't want to go through the derivation right now. So just accept this formula. But okay, this will be used a lot in our current chapter, okay, for Black-Scholes model. Why? Because you see the stock always has that kind of structure. So every time you do something with expectation of the stock, you will invoke this formula. So do remember it, okay? Anyway, going back to, right, applying this formula to this current situation, what do we have? Right, so to continue, it will be S0 e to mu t, right? Now, pay attention to, right? In the context of probability, t is a free variable. The variance is sigma square. Here is just for confusing reason, right? But not anything too confusing. Sigma here plays a role of t. Why? Because sigma is a volatility, okay? T here doesn't mean time. T here is just a free variable, the moment generating function, right? So sigma square here is t. So in other words, basically, after you apply the formula, you should get 1/2 sigma square times t as your answer. So in other words, right, we get the expectation of the stock price right here is this expression. Or if you want, is S0 e to mu t plus 1/2 sigma square t. Okay. And you see, like, some kind of remnants, okay, of the saving account kind of model here. This is just the logistic growth, right, of something, of a saving account with rate mu. So this is the rate of investment, the rate of growth mu in terms of the stock, right? The stock has has the return rate mu. That's what we're saying. Any question? And so to demonstrate to you why, right, this is the risk neutral model. You see that if we assume that the stock price is ES0 e to r minus 1/2 sigma square times t plus sigma w tilde t, okay, then what is the expectation of the discounted stock price? Now you remember, right, the whole point of risk neutral is that if you discount the future value, you should get the current value. So in other words, if this model is a correct risk neutral model, the answer for here should be S0. Okay, now let's see that the calculation works out that way. If we discount, right, then this term cancel. So you get okay. So you factor out now finally observe that we just say, right, the expectation of this guy is this. So in other words, it's going to be which is exactly S0. Okay. So this calculation is very routine, very easy, but you must know and you must use the moment generating function formula for the normal. Okay, that's what I want to point out. Any question on this? What about conditional expectation, right? What about conditional expectation? Because conditional expectation will be also involved, right, in our calculation for pricing at all the times besides 0. So in other words, suppose you want to have, let's say, for s less than t, right, condition of, let's say, no, let's say for t less than u, expectation of, let's just make it simple because the other terms are constant anyway. What about e to wt condition on e to wu condition wt? Like this. Okay. So again, right, pay attention. If I have no conditioning, suppose I want to do this only, then this is simple. The answer will be e to the 1/2 u. That's it. Coming from, again, right, this formula. But with conditional expectation, what do I do? The key, okay, the key to almost all of this calculation is to use the independent increment of the Brownian motion. That is, you always write, if you have two time variables like this, one is less than the other, you always write the future time, right, as the previous time, the present time, plus the increment. Okay. Future, present. I mean, by present, I mean, right, because you're conditioning on it. You think it's present, and this is the increment. Or rather, right, future increment. Okay. So the reason is the future increment will always be independent of the present value. How so? Because the present value can always be viewed as the present increment from time zero, because you can always put it like this, Wt minus W0, right? So the present value can always be viewed as an increment, right? The increment from time zero. Okay. So for that reason, future increment is always independent of present value. And remember, in conditional expectation, if you have independent, you can just ignore that, and there's no conditioning at all. So in other words, right, in this kind of calculation, you do e to wt minus wu, sorry, e to wu, condition on wt, there I do tilde, I forgot tilde. Okay. So will be expectation of e to w tilde t plus w tilde u minus w tilde t. Okay. Now you're conditioning on this guy, so it's a constant. If it's a constant, it can come out of the expectation. Now, this is independent of this. That's where I use the independent. Okay, they're independent. Therefore, you don't need the expectation. There's no condition. Conditioning is equivalent to no conditioning. But then you know what this is, because this is like expectation of a normal with mean 0 and variance u minus t. And then you apply the moment generating function formula, which gives you e to 1/2 times u minus t. And that's the answer. Any question? All right, let's do one more example. And this time, let me drop the tilde, all right? Because when it comes to Brownian motion alone, we don't need to distinguish between, we just do calculation of Brownian motion. So we don't need to kind of really emphasize that we're in the risk neutral context. So let's say for s less than t, I want to compute expectation of Wt square condition Ws. Okay. So again, right, notice that all the calculation that we'll be doing, if there's any conditioning, it always has a flavor of the future value condition on the past value. Okay. You could mathematically ask the question, ask the reverse question. In other words, you could ask for, let's say somehow you observe the future value, okay? But you don't know what the past value is. So you want to guess the past value based on the observation of the future value, all right? Now, this is a much harder calculation than this, okay? So we will never do this kind of thing. Not what would never is not right, but we will not consider this kind of calculation in this class, okay? But the time flow here really matters. You can ask question on both directions. One direction is hard, one direction easy, okay? Now, of course, easy as in like there's a way to do it, but you still need to master it, okay? And the way is, again, to split the future into the present and the future increment. Okay. And you manipulate, but in your manipulation, you always want to keep the present and the future increment as a block. You do not want to mix things like this. If you mix things like this, it becomes meaningless because this has no meaning in terms of conditioning from the present point of view. So you will expand this square, keeping these two as two blocks. So in other words, this will become is that okay? Now, right, you use your conditioning rule. Because you condition on WS, you know what WS is. Therefore, expectation, right, it's just like itself. So in other words, this is WS square. Oops, sorry. This is WT minus WS square. Okay. Plus, okay, this is known, so it comes out. And the last part, for now, let's just keep it like that. All right. Any question on this? Now again, right, this is very precise stuff. So do not make any kind of wishy-washiness on this. I've seen more than one time students trying like this and think it's the same. It's not the same. Okay. Writing WS square and expectation WS square are very different. Here, this is a random variable. It's a random variable. Okay. It changes every time you look at the event again. Every time you look at this event again, you see a different value of WS. But when you write something like this, it's a static number. It's S. So every time you look at that, it's always S. Okay? It's not the same. The point of view is we're conditioning on WS. So it must be a random variable based on WS. Okay? So it's not the expectation WS square. It's just WS square. Because WS, we know what it is. Anyway, so to continue, you then use the independence of future increment and present value, giving you or allowing you to not use expectation. Oh, sorry, to not use conditioning, because this and this are independent. So conditioning or not doesn't really matter. Or conditioning or not is exactly the same. So that becomes that. Finally, okay, recall that WT minus WS is a normal with mean 0 and variance T minus S. This becomes WS squared. This is 0. This is the second moment, but the second moment is the variance plus the square of the first moment. The first moment is 0, so the second moment is just t minus s. And that's the answer. Any question here? So I'm not sure you're referring to a different calculation. You refer to this kind of calculation up here? Because when if we're involved only with Brownian motion, right, then the stock doesn't enter. You understand? So the stock is like the random part that drives, sorry, the Brownian motion, right? The Brownian motion is the only random part that drives the stock, right? The rest of the stock model, at least for Black-Scholes, are constants. So as far as expectation is concerned, right? You see, every time you do expectation on a stock, you essentially just hit on the Brownian motion itself. So when we ask question, might as well just ask on the Brownian motion part and ignore the stock part, because that's just, decoration. Okay, I'm not sure if that's what you're asking, but here in the Brownian motion part, there is no S involved, because basically we're just interested in doing calculation with the noise part itself and seeing how the rules apply there. Yeah, but of course, I mean, like when you do calculation with the stock, S naught might involved or not. Okay, it depends, because remember when we do expectation, when we do expectation, what that means is implicitly we are conditioning on the time 0. And so that's why it's natural for the stock price at time 0 to show up. But for example, right, I don't have to. Suppose I do, that's what I was trying to do before, and I think it's too much decoration, so I dropped it. But I could have done the stock price at time u condition on the stock price at time t. Okay, so let's do that. Actually, for example, suppose I want to do this. What do I get from this? Now, let's say supposing I take the simplified stock price model, which is ST to be ST to be S0, e to the mu t plus sigma w tilde t. Okay, let's take this model. How do I do this calculation? Well, actually, the idea of the Brownian motion that I just talked to you about applies here. In other words, because the present time is t, you still want to express the future in terms of the present. Okay, dragging the knot in here is very, very inefficient, and it doesn't help, because the 0 here, you understand, is before the past, right? It's like this, right? So if you drag the 0 into this expression, it's useless, and it might lead to wrong calculation. So in other words, the trick to do this calculation is also to start from ST and see how you express SU in terms of ST. How do you do that? Well, I hope it's not surprising that this is the answer. Do you understand? And so in this particular calculation, ST is a constant. Yeah, it's cool, but when you, from a certain point of view, you should appreciate this is perfectly natural. All right. I know from the symbolic angle, it's like tedious and crazy, but from a intuition point of view, it's very straightforward. You're dealing with calculation from time t. Dragging the point 0 in is irrelevant, I insist, right? And so starting from t, right, and look at the increment into the future, for me is very natural, all right? But of course, pay attention, right? This is w tilde, sorry, this is w tilde u minus w tilde t. Yeah, okay, that's all. Now st is a constant because you are conditioning on it. So you drag it out. Also the return, right? The return part is constant. So you take it out. And then you get left with this. But now you recall that what is ST? ST basically is driven by WT, W tilde T. So it's exactly the same story again about future increment is independent of present value. So exactly that this conditioning is the same as no conditioning. Right? But you see why I just did example with prime motion, because that's exactly this calculation right here. With decoration, somehow to bring in the ST in. But so that's the Black-Scholes point of view, that the stock has two components. There's a growth component that's purely static, purely deterministic. And that's the random part, which is driven by the prime motion, which you should understand. And that's what we will spend a lot of time explaining, right? But the transition from prime motion to stock is usually just a shifting by constants kind of stuff that algebraic, but nothing worth, our discussion about. So to give you the answer, oh, sorry, there's no E, right? This is little e. The final answer is that. But also, right, I think in terms of your question, it's not S0 here, it's S little t. Okay. Any other question? Okay. So now this is the basic, basic probabilities that will be involved when you deal with the Black-Scholes model. And in your homework, right, this week and next week, you'll be asked to do more with this kind of calculation. So now let's go back to the story of the stochastic calculus, okay? Where somehow, right, part of the explanation that will be derived is to explain why the percentage return will always be higher on average, right, in terms of average, than the log return. And it has to do with this thing, all right? That, so first of all, let me just talk about something called adding, or rather, really is integrating with respect to prime motion. Or the top topic here that under the generic umbrella is called stochastic integration. Okay. So let me just demonstrate the financial idea behind this and why do we bother, right, discussing something very mathematical, right, very abstract here in this class. The reason is this, okay? So your stock, right? Your stock, let's say, okay, if you trust me, okay, that the percentage return, okay, I ask you to accept this for now. Let's say the percentage return also follows some kind of model like this. Okay. Now, I warn you, okay, for simplicity of discussion, what I say here and what I say above are not exactly consistent. In other words, right, I said that the percentage return must have this factor, because in comparison with the log return, it's not the same. But in what I'm going to discuss below here, what I'm interested in is about the aspect of stochastic calculus. So I just use the same letter mu, okay? I don't want to introduce more letters. That just makes it more complicated. But right, this is not the exact factor in relation to, say, log return and that kind of thing. Anyway, okay? But if you ignore that, then what I'm discussing here is quite routine. Again, what am I claiming? I'm claiming that the percentage return, okay, why is this percentage return to begin with? Because remember, right, this can be viewed as st plus dt minus st over st, okay? And well, that's a change in the stock price, right, in the split second divided by the original stock price. So that's the percentage return in the split second. So the percentage return on average has rate mu, has some rate of return, I don't care what that is, and has some volatility factor, right, that also is affected by the market noise. So, but if you shuffle this around, this says that the change in the stock price differential, is this. Okay. Now, is this magic? Is this magic shuffling? Well, if you view it from the differential angle, that's fine. That's perfectly fine. The reason is basically this is just a change divided by a static stock price. So if I multiply it over here, I'm fine. So what I'm saying is the change in the stock price, okay, at the moment will be amplified by how the stock price at the moment is with the return rate, which actually is a pretty interesting observation, which is true, which kind of says that the higher the stock price, the higher the swing in general in a split second, which is true. Observe it, right? I mean, by the way, right, don't confuse this with percentage. People usually report, like, let's say Amazon drops 1%, 2%. From that point of view, Amazon is not very different from, I don't know, let's say Microsoft or Starbucks or whatever, okay, which has lower stock price than it. But if you pay attention to the swing of like the actual numerical value, 1% of Amazon can easily be 10 bucks, right? But 1% of Microsoft could be like $2. Okay, so that's what we're saying, and that's just that idea. That in terms of numerical value, okay, higher stock price leads to higher swing. Perfectly simple. Now, okay, what do I want to do with this? Suppose I invest in the stock, okay? Suppose I have a portfolio. Not replicating, nothing, okay? Just a portfolio. However you want to do that. So basically this portfolio would be denoted by delta T, which report the number of shares of the stock that I hold at time T. Okay. So the picture is like this. Here, right? At time T, you hold this many shares. At this time, right, the stock price has moved from T to T plus dt, right? The stock price has moved. So your net gain loss in this investment period will be delta T times ST plus DT minus ST. Okay. Now, let me say this, right? So introduce another notation, pi t, right? Which is delta t times st, which is the value of your portfolio at time t, okay? Then, what I'm saying, right, is exactly what I'm expressing is the change in the portfolio, right? Net gain loss is the number of share you held at time t times the net change times the change in the stock price. Very simple. Any question on this? Now, if I push this dt to 0, or I go with the differential notation, this says that the d pi t, right, a differential in the portfolio, will be delta t times dst. Okay. Now, I will add, right, all the differentials up. I will add all the change to give me the net change. Okay, so I want to know, right, basically how much have I gained lost during the whole investment period from time 0 to time little t. Well, it's going to be pi t minus pi 0, right? This is the whole, gain loss during the whole investment period. Let's investigate what happens on this side. Well, what's delta u stays the same? What do I know about the movement of my stock? Well, here, right, from the rule of the percentage return, I figure out the movement rule of the change in stock. In other words, it will be mu times the stock price times the time differential plus volatility times the stock price times the shock in the market. Okay. That means that I can view, right, the return, sorry, not the return, the net gain loss of my portfolio as two pieces. The first piece is like the time investment piece. And the second piece is the shock from the market. Okay. So this piece is pretty tame. Basically, it is what you usually kind of think about when you invest in a stock, because how many shares you hold, the return, the stock price, the time differential. This is the good old return that the good old net gain loss that you think about. This is exactly what makes investment scary or not. Depends on who you are, because this is the prime motion. This is a shock in the market. Okay. This might be a swing, right, in your favor and you become rich, or it'll be negative and then you become, really you lost all your money, whatever. But the point is, right, from a mathematical point of view, this is what we call the Riemann integral, which has been dealt with before, or you learn in calculus. Just add stuff up as usual. This right here is called the stochastic integral that we need to discuss. Okay, or actually it's going to be in this course called the Ito integral. Okay, so again, basically the time piece, okay, the investment, the usual return is well understood, and we just let classical calculus tell you what to do. The shock from the market is a new one, the Bryan motion piece that needs to be taken care of. It needs to be discussed, and that's exactly what we're gonna say a few things about. Okay, and that's kind of falls under the umbrella of stochastic integral, stochastic calculus. And again, right, I want to say that. So basically, stochastic integral starts out with how to look at something like this, where W is a Brownian motion. And the point is, you see, it's naturally related to the value of a portfolio as you invest in the stock. As long as a stock is driven by the Brownian motion, then the movement of your portfolio also will be driven by the Brownian motion in a less understood way. All right. And so we want to discuss that. Any question? Okay. So let me explain to you, right, why this has to be isolated and has to be treated under a different framework. So let's remind you of what Riemann integral is about. So Riemann integral is to make sense out of this expression. And well, the classical picture you learn, right, is that you have a function, right? This is your function, which is, right, for all intended purposes, think of it as something in time, right? And hold on, right? The Riemann integral say, so you want to find the area under the curve, right? And the Riemann integral say, well, right, chop this into so many small pieces, right, with length delta t. Or for all intent purposes, right, that's the dt that we have in mind in our discussion as well, right? Chop them up, and when you sum, right, these guys up and push the dt to infinity, that will converge to an object that you call, to a number that you call the integral, which you also claim is in some way the definition of the area under the curve. Okay. Emphasis on the word converge. As long as, you know, this guy is continuous, as long as, actually, it can be discontinuous at, you know, finally many points, whatever. But the point is that as long as this graph is nice, you're okay. So in other words, right, the stock price is continuous as long as you don't do some crazy scheme in terms of your investment. Let's say you invest in a continuous way, right? Your share never jumps up and down too many times. This is perfectly a well understood piece from the Riemann integral point of view. Okay, meaning well understood means that it converges, is a well-defined object. On the other hand, let's look at the same object, but instead of dt, I do dwt. All right. Now there's no longer any picture for this. I mean, there is picture, but not something I want to show you. The reason is, right, first of all, remember, right, what's the interpretation? Here's at each point, right, there's ft, and this is dt. So ft dt has a very convenient interpretation of the area of the rectangle, right? Approximately the area of the rectangle, right? No, it's not even approximately, it's the area of the rectangle, right? Below the curve or above the curve, depends on how you pick your point. But what is dwt, right? So you still pick, let's say at this point, you still pick the height, but the dwt will be lifted from the Brownian motion. Basically, it says take the value of the function, multiply with whatever the change of the Brownian motion at that moment. Okay. So in other words, if you really want to look at this in some way, hand in hand with this, you need a graph of the Brownian motion for that particular iteration. In other words, you have your Brownian motion and it something like this, let's say. Okay. Then let's say at this time ft, this is that, you must look at how the Brownian motion changed from here to here to multiply with the valid function and add them up. Okay. So you may say, okay, I don't see any problem with that. Let me just do this, right? Let's say WTI plus 1 minus WTI, right? Because that's exactly what you do. You take the Brownian motion value from the next point minus the value of Brownian motion from the previous point, okay? Let's say this is TI plus 1, okay? The issue is this, that if you do this, this sum will never converge. Okay? I mean, never is too much, but like guaranteed that you will not get a conversion for this. What's the reason? The reason, right, is because the Brownian motion is too jagged, all right? The Brownian motion at every time, every moment in time, it's almost like at every moment in time, it will twist and turn. It will shift. You know, like if you have ever seen any car that drives in a very weird way, they seem to speed up and slow down at every moment. Maybe that car is trying to drive in the Brownian motion way or something. But basically, right, the speed is not defined at any point. It never moves in a smooth way. Okay. So again, I'm not saying the Brownian motion path is not continuous, all right? It's continuous. You can draw it in one stroke of the pencil, but your pencil must be like, you know, like you're really hungry and your hand is shaking like crazy. So basically, the Brownian motion path is nowhere differentiable, and that makes okay, that makes this sum not interpretable in the regular calculus rule. Okay, and that's why it must be treated under a special umbrella called the stochastic integral. Okay. Any question on this? Okay. So if you were to take a advanced math course, right, in stochastic calculus, then the next topic would be exactly to go in and define how to do this kind of operation, which is not our goal here at all, right? Our goal here is to understand the rules and apply to the financial context. So here, right, I'm gonna, after explaining, right, the difficulties to you, I'm gonna just kind of wave my hand, right, and say, there is a way, okay, to define, right, the conversions for the sum for the partial sum. All right, in the mean square conversion, in the mean square conversions sense. All right, and what do you want to say here? In the mean square conversion sense, and that's it. And it's and the limit, right, still denoted by the integral from 0 to t of f of t dwt is referred to as the Ito integral of f against wt. Okay, so that's a bunch of writing to say that don't question this. It's not our place to explain how this is constructed, but there is a well-defined mathematical object that is interpretable as the limit of the sum that I discussed somehow. Right? I say it never converges. In more advanced mathematics, you must clarify in what sense you mean it converge or not converge. And so if you apply a more particular framework, okay, you can view that it indeed converges, but not in your usual calculus way, all right? So there is a way, obviously first discussed by a guy called Ito. So he got the credit and we call that the Ito integral, okay? Our goal here is to understand the properties or to state the properties of these objects and see how it's related, okay, to our goal, right? To the purpose of finance and modeling. It's not to discuss why, okay, or how this is constructed. Any questions so far? Okay, so like I said, what you need to know or what you're responsible for is things called properties of the Ito integral. Okay. So first of all, right, let's just repeat what we have in mind. What we have in mind is this, right? And if you want, take the motivation from the investment of a portfolio. We have a run motion piece, and we have another that comes from somewhere else. And we want to integrate one against the other. Integrate just means that you keep adding the value of one guy, multiply with the change of the other guy. Okay, adding the value of one guy, multiply with the change of the other guy, and add them up. That's what we mean by integration in general. So the two central objects that we have is something we call the integrand, right? The integrand, little f, and the Brownian motion, w. Okay. So first of all, right, the number one thing we want to say is the integral is a random variable. Is a random object, okay? It's a random object. What that means is every time you look at it, it'll be a different value. And what do we mean by every time you look at it? Every time you look at a different path of the Brownian motion, right? The Brownian motion, right, this time you look at is this path, but the next time it may be this path. Then another time may be that path, okay? So because it's different path for different time you look at it, this will be a random variable, right? Even if f is deterministic. Okay, let's clarify what we mean, right, by these letters. So the case where f is deterministic is this. The integral, you can take the integral of t dwt. Okay, so t here is deterministic. Okay, because every time you look at a function t, right, it's the same. The path of t is t. Doesn't matter, right? How many times you look at it, it's still t. Okay. And so as far as we're concerned in this class, most of anything that only depends on time will be deterministic, okay? Or should be, right? Actually all. So for example, this is also something I say is a deterministic integrand. What is a random integrand? A random integrand is anything that's based on Brownian motion. For example, this. This is a random integrand because the Brownian motion is random, or more simply, this is random integrand. Okay. So needless to say, deterministic integrand is much easier to handle and discuss, or we know more about deterministic integrand than random integrands. All right, we can say several things about both, but these two cases are different enough to kind of separate them out, and you see soon. But Ito integral, right, as an abstract concept doesn't care. Ito integral as an abstract concept says whatever integrand you choose, as long as, again, it's not too pathological, and trust me, that level of pathological you won't see in this class at all, then you can always make sense out of an object like this. And it will be a random variable. Okay. Any question on this? Two, okay. The expectation of this random variable will always be 0. The expectation of this random variable will always be 0. The variance of this random variable will always be expectation of the integrand square times dt. Okay. So again, right, some basic properties, but if you are not careful to interpret, you will go wrong. First of all, this is a random variable. So therefore, right, the concept of mean and variance apply to it. Okay. So what's surprising is that doesn't matter, right, what integrand you use, it always has mean 0. Actually, it's quite simple to see it actually, because the fluctuation of Brownian motion on average is 0. You can think of it like that. Okay, Brownian motion, the average change is 0. So therefore, when you add all this average change, you get, on average, you get 0. It's a random variable, so you can talk about the variance. So be careful, all right? I know that we'll kind of go through a lot of notations already, but this cannot be the DWT, okay? You may be careless and you may write something like this, which is completely wrong. I don't have to look at it twice. This is wrong. Why is it wrong? Because of number one, this is a random variable. So every time you write DWT, you will make it to a random variable. But variance, right, is a number. Variance of a random variable is a number. Variance cannot be a random object. So that's, it's a DT term here, okay? It's a DT term and not a DWT term. Also, this guy may be a random integrand. That's why you must take expectation to make sure, right, that it turns to be a deterministic object, because it's the variance of some random variable. Any question here? Okay, I'll do very quick examples with these things I show you, but let me tell you one implication for this kind of thing. One implication is this, all right? Let's look at the investment, right? So it says that a change in your portfolio, right, is this and this. You could take expectation, okay? And what it says is that the whole, on average, right, on average, the change in your portfolio does not involve the blind motion part, which is good news. But on the other hand, something very funny happens that basically because on average this is 0, I guess one implication is you cannot beat the market. Okay, at least if you use the Black-Scholes model. Okay, I'm not saying like how people believe it out there. Why? Because it doesn't matter what scheme you use, right? Here it doesn't matter what delta U you use, as long as delta U is not like they call it like an unbounded scheme where you keep doubling your bet. Okay, like you keep buying the stocks like double or something. As long as it's a bounded investment, meaning you have a finite fortune, because the average of this is 0, there's no way you can guarantee that it's going to be positive. There's no way you can guarantee it to be positive. Okay, so in other words, if a stock is driven by motion, there's no way you can make your return to be positive, guaranteed, because the expectation will be 0. All right. So in other words, remember something like this. Let's take the stock. Let's take the return, right? The return rate is mu dt, right, plus sigma dwt. So you can say this, that basically, hold on, maybe let me just do this. And we'll do the example next time. The conclusion I want to make is this: there is no way to select an integrand, okay, ft, so that the integral ft dwt is positive guarantee. And that's what it takes to guarantee you to make money if the stock is driven by blind motion. So in some way, I think it's related to arbitrage in a way. All right, but of course not precisely yet. But again, right, the model, right, this kind of thing has a mathematical implication that you cannot select a scheme to beat the market in this model. Okay, and I'll stop here. All right, and we'll do more examples next time. Any question? Okay, thanks. See you next time.